Hi everyone, in this example, number 15, we're gonna choose a combined heat and power engine to replace the broken, spoiled furnace of this process. This is a common situation. The furnace is broken. We must replace this utility. This is a heating utility, and we're going to want to use a cogeneration, a combined heat and power engine. And for that, we want to change the heat exchanger network for using the minimum heating and cooling. Then we're going to perform an analysis to knowing the minimums, and then choose with this minimum the right engine. We are also given some guidelines or some precision. The process must be revamped, change it, improve, to work with minimum heating and cooling for 20 Celsius minimum approach. And we must not include cooler 1 in the study. This cooler 1 is the condenser of the distillation column. The reboiler heater 1 duty is not a linear stream, but can be linearized in two chunks, 30 kilowatts from 150 to 190 and 200 kilowatts at 190 Celsius. We will use two streams for the analysis and then just one for the design. Also, as fuel, we're going to use natural gas that can be taken as pure methane with a combustion ratio to air, to the stoichiometric air of 1.5. It is using 50% plus air than the stoichiometric. This and the heat capacity as a function of the temperature is given to us in order to calculate the mass flow rate of the flow gases. We have also three engine choices, one Enerco, one Deutsch and one Past engines with the details. Well, first that all the data structure. Cooler 1 is not included, as said, and the present utilities cooling water and the furnace is not included. See that we are not including this stream, the cooling water, because it's the current solution, but perhaps not the best. And we are not including this stream, both heat exchanger from the flue gases for the furnace, because probably it's not the optimum solution. We're gonna just extract the needs for the process streams. This is made first from one hot stream from 150 to 40. This is the bottoms being cooled. The second hot stream is the side condenser that will be taken from 95 to 95. Starting temperature is not known, but the safe assumption is taking 95. That is the coldest temperature it can be and the more difficult to cool. This is the worst case for us. And the last hot stream goes from 85 to 40. This is the heads product. As cold streams, we have the reboiler, this bottom stream that goes from 150 to 190, and we know that this must be taken in two chunks, one from 150 to 190 and the other flat at 190. This is a variable temperature boiling stream that probably is linearized the safe side. And the last one, cold stream, is the feed from -6 Celsius to 150 at the entrance of the column. We have not intermediate temperatures, then we will take it as a constant MCP string, a linear one. This is the complete problem table with the enthalpy flows calculated at the MCPs. With this problem table and the 20 Celsius minimum approach, we can calculate the problem table algorithm, the grind composite curve. You have here 275.75 minimum heating and a 66.75 minimum cooling, with a pinch at 85 Celsius in displaced temperature. It is 95 for the hot streams and 75 Celsius for the cold ones. On this grand composite curve, we can dimension the flue gases stream, the heating stream, and choose the correct engine. Here, it will be done just for the right choice, that is the Deutsch TVG. For each of the flue gases supply, we have a starting T. For the Deutsch, this is the gas temperature 436 Celsius. But remember, because this is a hot stream, you must take down half the minimum temperature approach, this starting temperature. Then it will be represented as 426 Celsius displaced temperature. And now see, as steeper the slope, the less mass flow rate will be needed, because the smallest will be the MCP. So we can take down this stream as much as we can, and this is till it touches the grind composite curve. This is a utility pinch. This will give us a tight dimensioning for the heating, a narrow dimensioning that afterwards will be difficult to design. And now the calculation for the flue gases. As we have 2 points, we can extrapolate the final temperature, the outlet or stack temperature of these flue gases. This is 144.4 Celsius, not displaced, the real one. The displaced temperature is smaller than that. For this final temperature, you must check that the dew point is not reached, in order not to have an acid stack, a condensation of the flue gases. Well, the water content in these flue gases. Once we know the starting and finishing temperature, we can integrate the heat capacity and calculate the mass flow rate for the flue gases. That is around 2,922 kilograms per hour. This is a value under the nominal capacity of the engine, but no so far. This let us take this engine as the right one. The other two have their problems, or they have not the capacity, or this capacity is too big for the case. So we conclude that this engine is the right one, and we choose to buy this. Finally, you have here the problem table, the utilities stream table, the coordinates for the grand composite curve, the coordinates for the utilities grand composite curve, this is, and the combined grand composite curve showing both pinches, the utility pinch and the process pinch. And this is all.